Hi guys, can I get a sound check?
Yeah, I got you.
Sir?
Yeah.
Yeah, I can hear.
Hi. How did the quiz go, guys?
I think it was pretty good. It was interesting to see the student ID for the second problem. That was like a pretty interesting way to incorporate unique values for IS.
I was trying to come up with something creative, but I didn't have a lot of time. Next time I'll come up with something more interesting. Let's see, where were we? What is today?
The guard dog is awake.
Yeah, I moved to my wife's office last time to get away from the dog, but I got kicked out of her office. So back here, we are here. She's like 18 pounds, but sounds like she's 150.
Yeah. I was just gonna say, sorry for the whole quiz email confusion. I was having trouble sending it, and I accidentally sent copies of emails.
Oh,
sorry about that.
No problem. No problem. I'll sort through it. Hopefully, we'll get the grade scope working. But part of my problem is it doesn't show me what I'm like. At least I couldn't figure out. I don't get I don't know how to. I wish they could let you set up a fake student and send myself an invite and see what the problems are. But I guess you just have to know what you're doing. So we'll figure it out. No problem.
Cool. Thank you. Appreciate it.
Sure. Okay, let's get going, guys. Let's see. Where should I start? I think just a few notes from what we talked about last time. I think we said, look, if there's this circuit thing diode. Okay, and then sorry guys. So this is the anode. This is the cathode. And the anode cathode really, I don't even know what to tell you guys where this came from, but it's just a word. I always think of it in terms of P and N. Just helps me remember that. So we said if you could have an ideal diode.
Sir, just wanted to ask you a question, if you don't mind. So we're working with the ideal diode, whereas in the previous chapter, we worked with the whole natural log and exponential, which is actually how the diode acts, right?
Yeah, so we're gonna come, probably in this lecture, we're gonna come sort of a full circle. So the idea is this. Let me actually, it's a good question, because let me keep going back and forth. So let me just go over the whole idea. So the idea is, you have this semiconductor PN junction. And then it does this exponential behavior in voltage versus current. Okay, so that's something you can make. This is something real we can make. So let's call this a real device. And we find a ideal device. You just have to take my word for it at the moment that an ideal device, we think it would be useful for some applications. We're going to talk about those applications today, but let's say you would like an ideal circuit element. Might even call it a device at this point, called a diode. And then we'd like this to act like a switch that kicks. So in an ideal world, we'd like it to do this. For whatever reason, I'm just claiming that would be ideal. VI. So because we think if we had something like this ideal diode, we can do a bunch of interesting stuff. Like we could build like voltage regulators, different kinds of things that we'll talk about the different applications. It'd be useful. And then what we're going to see is that indeed you can basically use this thing as a diode, this PN junction. So a real diode. I want to call it a real diode. And we're going to show how it performs a little bit differently, obviously, than the ideal version of the diode we'd like. It has this exponential characteristics here. It has some back current or leakage current, depending on what you want to call it. So it's a little bit different. And then we'd want to see both on, like, we'd like to see how well it lets us approximate this ideal element that we like. And so these are all sort of a technique to introduce you guys to this concept. But basically what we'll see is you can, when you're designing a circuit, you can start with this really simple model, ideal model, and try to analyze your circuit or say, hey, I want this kind of behavior roughly, something that turns on at, when the voltage across it is greater than 0 and turns off when the voltage across it is less than 0. And then you can analyze your circuit and see, is this a circuit that's working the way I want or not? And then as needed, the experience you'll get hopefully from solving problems and looking at some examples of this chapter is when does it make sense to use this simplified model and stay with that simplified model? And when do you have to actually use this really complicated exponential model to get a better idea of how your circuit works? So I don't know if that answered your question, but it's like one of those things where you want something, but like the thing that you make works kind of like it, but there's some you can kind of model it to first order as the ideal thing. And a lot of times you can just stop right there, like it's close enough to the ideal element that it does what you want, but sometimes not. By the way, another thing to think about this diode circuit, it's very different than the other circuits that you worked with. So if you worked with say a resistor, I think I talked about this last time. Let's say if you've probably seen resistors and capacitors and inductors is what we've seen before. But if I plot voltage versus current of a resistor, I always have to do this. So V is equal to IR, so I is equal to V over R. So if we plot that, we'll have a linear line, and then the slope is 1 over R. Okay, notice I'm plotting V in the horizontal axis and I in the vertical axis. It's good to keep track of those, what we're trying to plot. But this resistor and all the other things you've probably seen so far, the key about them is that they're modeled by this sort of a linear equation, meaning that the characteristics don't change if you go positive in voltage or negative in voltage. The characteristics really didn't change, right? It's just the same equation regardless of what happens. You know, you can just stick that resistor in your circuit regardless of where the voltages and all that stuff is. It's a linear element, meaning that it's just represented by a linear equation. And the diode is the first circuit element we're saying that's nonlinear. You know, it's a non-linear, and the transistors will even get more interesting, but it's a nonlinear circuit element, meaning that if you look at this, where this is V and this is I, if you look at this part of it, say this is the behavior of V versus I. If you had a linear equation for this thing, you would never guess that when the voltage goes negative, it would do this. So it completely does something else here than it does here. So it's a very, very nonlinear. It's as like nonlinear as it gets in terms of an element. So I think that's the biggest thing that separates the circuit separates this class or the microelectronics from the previous circuit classes you've taken. Before, you were used to linear circuit elements. Here we're talking about nonlinear circuit elements. And first we'll introduce the new device, say like the diode, and then we're going to jump in to look at what kind of circuits you can make with that. And you can make interesting circuits. Okay, so let's see. So we have this diode. What else do I want to say about this diode? Again, the way it works is you can think of it as a water pipe. Okay, with I think that's kind of an analogy that I like, and it's got like a hinge kind of a thing. And then if water flows in through here, this hinge opens up. This hinge opens up and lets the water go through. Okay, that's if you were using your diode and you were operating when the N is more positive than the P, or when the cathode is or when the anode is higher than the when the anode is higher than the cathode. Okay, so basically it's an on circuit. It's like a switch. That's if you had a switch, so if you had a diode, the analogy in this case would be that it is a closed switch if you're looking at water current versus electric current. Okay, and then if you had the same hinged element, so I'm going to just redraw that. Now let's say what happens if the water tries to go this way. If the water tries to go that way, then the hinge actually closes on you. Okay, so it does not, the water just does, you can't run the water through that way. And again, if we have the analogy of a diode, basically what it looks like is an open switch. Okay, so here you have a closed switch, means that as much current as you want will flow through as soon as it turns on. And here you have a open switch, meaning that no matter how much voltage you put across a open switch, you're not going to get any current to go across. And
so when current is going through the anode, it acts as the closed switch. Sorry, I didn't mean to interrupt.
No, no. I was just actually thinking about your question. You know, I would, William, I think I'd look at it more. Yeah, I mean, certainly you have current. So if your question is, yeah, current likes to go this way, it cannot go that way.
Okay. Cool.
Does that make sense? Now, the reason I was thinking about how to answer your question is I kind of like to think of it more in terms of what the voltages are here and here as to whether current will flow, period, or not flow. But I think you're right. I mean, it does definitely flows this way and does not flow back that way.
So just in general, it's better when doing circuit analysis to use voltage polarities, right? Just in your experience.
Boy, that's usually how I think about it when we're looking at diodes. But that's why I was thinking, as William was asking me that question, do I want to say that? I'm not sure I'd like to say that it's better to do it one way than another. For example, when we get to bipolar transistors, which is the next chapter, I think you're actually kind of better. Well, like there you can definitely think in terms of currents as opposed to voltages and sort of start with a current and work backwards into a voltage. It might even be better. I don't know. So let's just put it this way. I usually think of it in terms of voltage usually, and then kind of derive the current off the voltage. But I might take that back at some point, even in this lecture. I'm not sure, but yeah.
That's cool. Thank you.
Yeah, sure. Okay, anything else in terms of a review? Let me see. What else would I like to say? Whoops. Okay. And then we used, let me just, I think we talked about this last time, but just to give you guys the idea again is that if we had now look just purely as like circuits, if we had a situation where we had a voltage source and a diode and a resistor. So this is a real simple circuit that's, it's easy to put it, you could even put it together in the lab easily. So let's say you had this kind of case, and then you wanted to sort of see what happens, the same analogy, okay? The way you'd look at it is, and then this is, again, you'll see when we analyze the circuits, we go back and forth between V, voltage versus current, and voltage versus voltage. At the moment, we're just talking about voltage versus current behavior. But like very soon, like maybe in about 10, 15 minutes, we'll start talking about voltage versus voltage. But so anyway, the way we would look at this guy in terms of this curve of voltage versus current is first we would think about what would happen if V sub A is very positive. So let's say VA is a very large voltage or is very larger than, I don't know, is large. It's greater than 0 for the sake of discussion. So this is still an ideal diode. So if V sub A is bigger than 0, we can say that this point is higher than this point, and we can say that the diode, so in that case, the diode looks like a closed switch, okay, when V sub A is greater than 0. And then if I draw the rest of the circuit, it's going to look like The resistor is the resistor. Okay, so out here, when V is positive, it looks like we're just like this circuit here. It's just a resistor. So when we're in the positive territory, we just see a resistor, that resistor R1. And because we have this equation and we're plotting I versus V, we end up with 1 over R as our slope here. And then let's look at this case when V sub A is less than 0. So that means that this point here is lower than this point here. Okay, in that case, the diode is, so in that case, the diode becomes an open circuit. And when there is an open circuit, you don't get any current flowing regardless of what the voltage is. So that when there's no current, you just end up on the 0 axis here. So this is here and this guy's out here. Okay, everybody, does anybody have any questions about that so far? This is kind of where we stopped last time. Okay, so we'll get lots of practice about this. So speaking of practice, let's try. So now, I'm going to ask you to consider something else, but use the same analogy. Okay, this time, as the example, I'd like you guys to plot 2 voltages. Okay, with a diode circuit. And the way the circuit looks is it's Vn, and then slightly different than the other one. We have a resistor here, and then we have a diode. And then we're looking at the V out here. So I want you guys to think about what V out versus V in would look like with this resistor and a diode. So I want you guys to spend a few minutes thinking about that. And then it's the same idea. You first think about what would happen if Vn is extremely large. Then would the diode be an open switch or a closed switch? And then redraw the circuit with the diode as an open switch or a closed switch. I would really encourage you guys to like actually redraw the circuit, because it just helps. Just go through that, do yourself a favor, go through that extra step of redrawing it. And then think about the Vn being a very negative voltage, then what happens to the diode, and then redraw the circuit for that as well, and look at it.
Can you scroll back up for a sec?
I'm sorry, Nicholas?
Can you scroll back up for just a sec? I missed what part of the thing.
Is this good?
Thank you.
Sure. Okay, guys. So let's take a crack at it together. So let's first look at the case when Vn is sorry to mix. I just call it Vn is greater than 0. So when that happens, this P side of the diode is higher than the N side. So I was going to redraw the diode. And in that case, if the P side is greater than the N side, then the diode is a closed switch. Okay. So if I was going to redraw the circuit here, it would look like Vn, I'm not gonna, okay, oops, sorry guys. Vn, and then V out. So we're out here, okay? So then Vn is positive. So let's say we have this circuit, which is, you know, Vn, there's a resistor there, but we're shorting V out sort of across Vn. So, or, you know, if you think of the Vn, if you think of both of these guys being ground, you're shorting.
Isn't it 0?
I'm sorry?
Isn't it 0 for V out?
Yeah.
Because of the circuit?
Exactly. So it'll just look like
Oh.
this. So it'll just look, so no matter what Vn does, V out goes to 0. So as you, if I was going to crank, if I was going to draw, V in versus I through R1, it would look like I'm dumping a bunch of current through R1, but V out isn't going to change because I'm plotting V in versus V out. So I keep getting current going through here, but because it's shorted, V out is shorted to ground. V out just stays at ground. So, okay. And then when V in, let's look at the situation where I can draw it out here. V in is less than 0. Okay. When V in is less than 0, the P side is lower than the N side, which means that I want to redraw the diode as an open circuit. That's not a very nice looking open circuit. Okay, and then I'm going to stick that resistor again, R1, and V in. And then V out, we're measuring across this open switch. Okay, so in this case, oops. So whatever happens, because V out is just floating. There's no resistor here or anything like that. It's just an open circuit. So there is no current really flowing through R1, and just V out just follows whatever V in does. Okay, so just here V out is equal to V in, meaning that if I was going to draw it out, V out would just look like V in. Now notice, so V in here is negative, so V out is also going to be negative. So the slope is just going to be a slope of 1. Okay. Anybody had any questions about that? Had a hard time following besides my handwriting here? So you just,
No,
go ahead.
Yeah, the only thing is I messed up on the VM being negative, but yeah, that makes sense.
So you kind of had it drawn like going up like this or something like
Yeah.
that? Yeah.
Yeah, I messed up. Yeah.
Yeah. So just So okay, what are the pieces of advice? Go to extreme ends of Vn, so very positive, very negative. Redraw the circuit, and once you've redrawn the circuit, then sort of try to write the equation for it. I think maybe those are the things. So it'll help you get across. But anyway, all of it, I mean, the main thing is practice. Well, if you guys practice, you'll see it'll start coming a little bit more naturally. Okay, so
Thank you.
Sure. So here's another example, okay, which is going back to, or this is probably one of the most important usage of a diode that you run into every day, but we talked about it during the last lecture. But basically, anytime you have a phone charger or PC laptop charger, you're plugging one end of that charger. So charger, you're plugging one end of it into the wall plug, and you're plugging the other end into your, say, cell phone, or let's say cell phone for the sake of discussion. Okay, and we said the wall plug is, as I'm sure you guys are familiar with this, is 110 volt RMS, 110 volt RMS, sort of maybe 150 volt peak sine wave, and it's purely alternating current, means it has no DC component value, and at 60 hertz. Or I guess this is time. So what I really want to say here, to be exact, is 16 milliseconds. Okay, so that's what we get going in. We're all familiar with that. And what your cell phone wants to see is something like, if it was, it's going to draw, it doesn't want to see change with time. It just wants to see a nice flat, whatever voltage is it. I think we said 3.5 volt. And somehow we got to go from this AC to, so this is purely DC or direct current. Somehow we want to go from this AC to this DC voltage. And we said, it's easy to reduce this 150 volts to something like 4 volts or something like that for the sake of discussion. But we needed to do something more creative to get a DC component off of this. So if you integrate an AC signal over time, it'll have 0 DC component, because this, if you add all of this to this negative energy or current, you'll end up with 0. So what do? So this is where, and we said something that's useful is a diode in the circuit, and it would be useful if we could cut out, if somehow we could cut out this, no, don't do that. Let's see, I guess I just have to redraw it. Should have been smarter. Let's say if we just, let's say we cut out the negative parts of this and we just ended up with the positive cycles.
Do we use a filter to do that?
So what to get rid of the negative parts?
Yeah.
What kind of filter are you thinking of?
I'm thinking a low pass filter.
Yeah, so what the low pass filter does, let's think of a low pass filter. The low pass.
We need sorry. No, I was just gonna come to, we need a wave rectifier, correct?
Yeah, we'll need a rectifier. Yeah.
A bridge rectifier. made of diodes and capacitor.
Yeah, you need a diode circuit. But let's for the sake of discussion, let's think of the filter, right? So what does a filter do? So you know, like a really easy low pass filter is like an RC device. So V in, V out. So what a filter does is in the frequency domain, if you have amplitude here, or a low pass filter, what it does is it passes, assuming I put the log of amplitude or something like that, amplitude. What it does is it would pass signals that are low frequency, and not, you know, the signals that are high frequency would get attenuated. Okay, so that's a low pass filter. Now notice something here, that if you look at this thing in the frequency space, because it's a pure sine wave, it'll only have a single frequency, and the single frequency is, so its frequency is at 1/16 milliseconds or 60 hertz. So this signal will, depending on the low pass filter you use, will either be, you know, depends on what values you pick for this or this, will either be here or here, okay? If it's here, then it really doesn't, the low pass filter doesn't do anything to it, right? If it's over here, then the low pass filter would basically attenuate it. So you would go from this kind of thing to your output looking like an attenuation, depending on where that filter pole is. So you can reduce the amplitude of the signal with a low pass filter, but you won't be able to cut off, like you won't be able to cut out the negative parts. The negative parts will still be there, but they'll be exactly the same amplitude as your positive half, just both sides would be attenuated. And the reason for that is because this circuit is a linear circuit. It's gonna do, or you know, a circuit like it, an RC circuit or something like that, it's gonna do exactly the same thing to the positive, sort of positive amplitude part of your signal as it'll do to the negative amplitude part of your signal. Does that make sense, Elvis?
Yeah, I get it.
Yeah, so you can reduce the amplitude, which is something we do want to do. And you know, we said we did that last time with like coupled inductors. I guess you could use a filter to do that too, but it's still left with this problem that even the filtered value doesn't have a DC component. And so if you do want to get to a DC component, you need this thing called a rectifier. So, actually I looked up this word rectifier, and I have no idea where it came from. It just, you know, if you look at the Wikipedia or whatever, Circuitopia or whatever the heck thing it is, rectifier means to rectify a situation, to correct a situation, which is kind of meaningless. So I just think of it as a word, like the fact that it's, you know, a rectifier or rectifying a signal doesn't really mean anything. That's basically what it's doing, is basically what a diode does, is it's taking something and getting rid of, like again, we're, instead of going high, which, how do I draw this? So it's by rectification, we're sort of allowing half the one polarity of the signal go through and not the other polarity. So that's that's one of the prime, whoops, that's a bad idea. That was one of the prime uses of diodes is rectification. So, and let's look at what that looks like. Okay, so let's say we had a voltage Vn. And notice I'm putting the diode here in this case. And then I put a resistor here. Okay, and I'm going to call this V out. Okay, so let's, once you guys take a crack at looking at what V in versus V out looks like in this case. So again, remember the points were look at extremely positive Vn and see what if the diode is on or off. Look at extremely negative Vn to see if the diode is on or off. And then redraw the circuit in both cases with the diode as a switch that's either on or off. And then sort of, if it helps you, write the equation so at that point, so you don't get it wrong, polarities, etc. And then try to draw the response. Give it a shot. Okay, guys, let's take a look at it. So let's think about the case when Vn is greater than 0 or large, okay? So in that case, the P is higher than the N, meaning that the diode is a closed switch, so I can draw the diode like that. Okay. And then I have a resistor R1. In, V out. So we're talking about this part. So now because the switch is closed and there's a resistor here, I get a current across the resistor as Vn goes high and low, but V out is just shorted to Vn. So basically V out is going to end up being equal to Vn. So basically what we'll get on the, when Vn is positive, we'll get a slope between V out and Vn that has a slope of 1. Okay, and then when Vn is less than 0, the P side is less than the N side. So the diode is an open switch. I'm going to draw it as an open switch. And in this case, Vn is not connected to V out anymore. So it doesn't matter what Vn does. And V out is just a voltage across a resistor where there's no current flowing through that resistor because Vn isn't connected. So basically V out just is equal to 0. The two ends are the same. So we'll end up with that. Okay, and then look at what this is doing. If we look at this V out versus V in curve, if we have a sine wave as the input to this circuit, so let's say here we had this sine wave. So this is the input. Oops, yeah. This is the input. When the input is positive, so this is time, and so the black is Vn. I want to draw red as V out, so voltage. So when Vn is positive up out here, so when Vn is positive, V out is just equal to Vn. So it's just equal to Vn out here. Okay. As soon as Vn goes less than 0, so anything here, then V out is just 0. So V out stays 0. Then when the cycle repeats, V in goes positive again, and as soon as it goes positive again, V out follows V in again. So this is doing what we said would be like a nice to have as a starting point to get our DC voltage, which is to get rid of the negative values. Okay. And this kind of action is called, in circuit design, is called rectification. And this type of circuit is called a rectifier. Go ahead.
Quick question.
Yeah,
so if you connect the diode backwards, you'll get rid of the positive side, and now you'll get the negative side as an output. If what I meant is if you flip the diode.
Yeah, let's try it. Let's give it a shot. So you're saying if we hook it up like this.
Exactly.
Okay, let's see if we can do this. Okay, so we want to plot V in versus V out. And let's say we look at V in is greater than 0. So this side is higher than this side, meaning that the diode is open. Oops, the diode is open. So basically, V out is just sort of across this resistor with no current. So no matter what V in does in this case, V out is just 0. Okay, and then let's see. If Vn is less than 0, oops, let's draw a diode. So if this point is lower than this point, then the diode is on, or is shorted, yeah. Or switch is closed. You got resistor. So in that case, V out is just following Vn, in which case you get this with a slope of 1. Is this what you'd imagine, Manuel?
Yeah, something like that.
Yeah. So in this case, like I think you'd imagined, if you hook it up like this, what it'll look like is, if you look at what it does to the sine wave, that this being Vn, it would, anything that's, every time Vn is positive, it'll be 0. And then as soon as Vn goes negative, it's gonna follow it.
Yeah, exactly that. That's what I was thinking, if that's possible. Like if you flip it, then you get rid of the positive, but gaining the negative.
Yeah.
Okay.
Yeah. So, you know, I don't know why, but I like have a 50-50 chance of always getting these things wrong when I don't actually write it down. So that's why I wasn't even trying to give you guys another example. When Manuel asked me, I was like, oh crap, like I better work it out. Because no matter how simple the thing is, when you're looking at diodes and stuff like that, a lot of times I get wrapped around the axle and confused about what it's going to do. So especially in front of an audience like you guys, I'm going to try to work it out in gory detail to make sure I don't get it wrong. So just sort of,
Thank you.
that's a piece of advice for you guys. And I kid you not, I get it wrong half the time if I try to guess at the answer. Okay, so we have this rectification. Okay, so let's look at an example that's, you know, the book gave as one particular example we could use for this is something called a signal strength indicator. So for example, let's say you've got your cell phone on and, you know, we see those bars lighten up. Okay. So those signal bars are an indication of how strong of a signal you're receiving from the tower. And so question like, let's see, how would you make such a thing? Okay. Now, remember that when you're talking about a signal between the cell phone and your phone, you know, there's an antenna, there's a transmit antenna, I'll just draw it like that, in the tower. You get this radio frequency signal, and here's your cell phone. This is cell phone, and this is antenna. Sorry, this is the tower, let's say. Okay, and I think we talked about this in the very, very first lecture, but because you want to have a reasonably small size antenna, the antenna is proportional to your wavelength of this of whatever signal you're transmitting. And so because you want your antennas to be short, like your antenna in your cell phone, you'd like it to be, let's say 10 centimeters or something. That means you'd want the signal, that's your cell phone signal, to be in the gigahertz. So you want a very short wavelength, okay? Otherwise you'd have to have a really big antenna. So what you do is you have your, I don't know how to draw it, but let's say you have your microphone and you multiply that out by a really high frequency signal, like a multi-gigahertz, say gigahertz, or what's 1.8 gigahertz. Well, it depends on what carrier and all that stuff, I guess. But basically what you have is you end up with a modulated sinusoidal signal going to your phone. So that doesn't really have any DC component on the average, but it's a cell phone. This is it's a sine wave, okay? And then depending on how the distance between the tower and your cell phone, you could get a really strong signal. You can get all your bars lit up, or you have, when I erase everything here, probably that's going to be ambitious, or you have fewer bars lit up. Okay, so you want to basically, let's say you want to make a simple circuit that would create that. So what you can do is you can make the signal strength indicator, and you can basically rectify, use the same circuit we showed. So basically in let's say just for the signal strength, we give it another path from the input, and we put a diode there and a resistor like we did. And this is the goes to your, whoops, sorry guys. This goes to your whatever, your bars, let's call it, on your cell phone. And what that does again is you've got your input to your from your antenna is like this, and your output that goes to your bar indicator in this case would be like half of this. Now notice something interesting, by the way, which we'll come around to, is time. You could get a signal like this if you're really close to the tower, or you could get a signal like this if you're far from the tower. Your amplitude would drop significantly, but in either case, your rectifier is going to cut out the lower half. Okay, so let's see what happens if somehow, and we'll see this a little bit later, but for the sake of for the sake of discussion now, let's say you had something where you could integrate this. So integrate the signal over time. Okay, so basically your input is something like, so Vn is Vp. So let's say this is, in each case is Vp, sine of omega t. Okay, so it's a purely sinusoidal input. And your V output after the rectification, okay, it's either when it's in the positive half, okay, your output is going to be exactly like your input. So V output is Vp sine of omega t as well, but only when t is between 0 and t over 2. So this is the total period, t. So only in this period does your output equal to your input. And the rest of the time, V out is equal to 0. So when t is between t over 2 and t, v out is 0. And let's integrate that, okay? So if we took an average value of this by integrating it, so v out average is we are integrating the signal, or taking the average, yeah, between 0 and t, v out. But because v out is different between 0 and t over 2 and t over 2 and t, what this is equal to is 1 over t. And then look at 0, from 0 to t over 2, you end up, I'm just plugging in the numbers from up here, v pi sine of omega t.
Professor, I have a question.
Yeah.
What does it say on the v out ay, or what is it? Left-hand side of the integral?
Oh, here?
Yeah, that one. What is
Yeah, sorry, I was trying to say average, AVG.
Oh, okay, so v out average, got it. Thank you.
Yeah, sure. So what I'm doing is I'm integrating over the whole period and dividing by the length of the period to get the average value. Okay, so plus from t over 2 to t, v out is just 0, so plus 0. Okay, so we end up with this, just this first half. And then if we integrate, we end up with 1 over t vp minus cos omega t. Whoops. Okay. So now let's think here. Make sure I don't get this wrong. But omega t. So omega is, I believe, 2 pi over t.
Professor, quick question.
Yeah.
What's VP again?
Sorry?
What's VP?
VP
Yeah.
was the peak value of our input. So if you look at, we just said our input has this equation. And if you're very close, so it's the input is V sub P sine of omega t. So
Oh, I see from the graph now.
yeah. So basically, if you're close to the cell tower, your VP is large, whatever that is. We'll look at what large means in a cell phone environment. And if you're far from the tower, your VP is going to be much smaller. But the sine of omega t will always be the same. It's always riding on the same frequency sine wave.
Okay, thank you.
Sure. Okay, so this is equal to 1 over t vp minus, so let's see, omega, this omega t is gonna be, so it's gonna be, let's see, minus cos of, let's see, omega t is 2 pi over t, t over 2, minus cos of 2 pi over t, 0. So let's look here at cos. This guy goes away. So you're talking about cosine of pi, okay, which I think is -1. Okay, and here's the cosine of 0, which is 1. So it's -1, -1. And the whole thing, the minus. So this, because these all cancel each other out, then this becomes 2. Okay, so you end up with VP over, or 2 VP over, sorry, what am I doing wrong here?
I think you may have forgotten to divide by omega when you integrate it. So the integral should be negative cosine omega t over omega.
The
Maybe?
chain rule, right?
Yeah.
Is that right?
I checked on the integral calculator because I also forgot. But, yeah.
Really? Because I thought it would be over. Yeah, I'm clearly forgetting something. Yes, thank you. You're right. So here we end up with omega here. Darn. So 1 over t VP over omega times 2. Okay. And then we plug in, thanks for catching that. So I'm going to plug in 1 over t v sub p over 2 pi over t 2. So the 2's cancel out, t's cancel out, so you end up with vp over pi. Okay, so that's, so now once you take an average of this rectified sine wave, once you rectify it and you take an average value of it over time, then you get something. So like, it's probably not a good idea to do this, but you could light up, you could sort of get a signal that's now a DC value, okay, which is VP over pi, that's proportional to your signal strength.
So VP over pi is now a DC signal, right?
It's a DC signal. Yeah, it's just a constant value.
Oh,
I mean, it's
okay,
a constant value depending on VP. So if you're sitting close to the tower, VP is a large value, and then you end up with a constant large value. And if you're far from a tower, you'll get a constant low value. So let's take a look at, let's see. I think we've got an example of, okay. So let's throw in some numbers here from the book. And so it says, okay, in the case of a cell phone, so it's saying the frequency is it's not quite, this is the angular frequency, but let's say the frequency is 1.8 gigahertz. So the frequency is 1.8 gigahertz. That's a carrier frequency of your cell phone, okay? And then this is the amplitude range that your phone can handle. Okay, so which is kind of scary. It goes, when you're close to the tower, the max you'll get is 10 millivolts. Okay, when you're far from the tower, the maximum, so this is equal to V sub P sort of max. And the lowest signal that your phone will sort of recognize as a real signal is 2 microvolts. So VP min, that you'll be sort of recognizable, whether you still get anything. Okay, and so what happens is if you plug this in to your rectifier and look at the signal, so these would be, will go from 10 millivolts over pi, which is equal to 3.18 millivolt to, so this is your max amplitude for your signal strength indicator, to the minimum would be 2 microvolt over pi is 0.637 microvolts. Okay, so these are the ranges of values that you might get as your signal indicator. So sort of a couple of interesting things there. And a couple of interesting things about RF signals and cell phones in general. One thing is you look at how small these signals are. I don't know if you guys ever worked with signals this small or seen them in the lab, but because there's like a lot of noise and electronics. So, you know, it's very difficult. Look at how small that is, 0.637 microvolts at 1.8 gigahertz. Okay, pretty small signal at high frequency. Higher frequency usually means more noise. Okay, so one thing, the first thing that comes to mind is how small of a signal you're dealing with by the time it gets to your cell phone or gets from the cell phone to the tower. It's pretty amazing. The other thing, which is amazing, is how huge the difference is. So this, you could think of this as the dynamic range. So between 3.18 millivolts and 0.637 is like 3 orders of magnitude difference in signal levels. So, you know, it's a huge difference, you know, 1,000 times difference, more, 3,000 times difference between the lowest signal you get and the highest signal you get. Okay, which is just, again, both of those things, both the amplitude being so small and the dynamic range being so high is just, you know, it's amazing to me. So it's pretty amazing that this stuff works. Okay, so that was one use of a rectifier, is this signal strength indicator. Let's do one more thing. Okay, let's do an example of real quick. Sure. Okay, let's do another example. Let's do a diode. So here's our VN. Well, let me first describe to you what this concept is. Let's say if we did the same thing. Okay, let me do it this way. Let's say we look at first our usual circuit, which is our, let's say if we had a diode, we had a VN just across the diode. And when we looked at the voltage versus current characteristic of that. VN versus I of the current of the diode. We know when the input is positive, you get a lot of current. When the input is negative, you'll get no current. Okay, so basically that's what you get. And we've seen this. We started off the lecture with this. Now let's say I change the circuit a little bit and I add a battery in series with the diode. So that's like a symbol for a battery. So a battery is just a voltage, so it's a constant voltage source. And let's say the battery is 1 volt. And I have this VN. Okay, so what happens then, if I draw VN versus I sub D1, is notice when VN is positive, it's still, because we took this, the N side, to +1 volts using this battery. So just because Vn is positive, now the diode doesn't turn on. It only turns on when it's more positive than the N side. So it's going to delay, it's going to turn on when Vn is equal to +1 volt in this case, right? So because it doesn't matter if the Vn is positive or negative, it's important if this side is more positive than this side, okay? And because we made the bottom side, the N side, +1 volt, then Vn has to go all the way to +1 before the diode turns on. And when Vn is less than +1, you end up with the diode being off. Okay, so it's exactly the same characteristics, but we shifted the diode value up by 1 volt. Okay.
Sir, should it be greater than 1? Because otherwise you're having zero voltage and you pretty much, I know you're referring to an ideal diode, right?
Uh-huh.
But still it shouldn't be like greater than 1.
If Vn is greater than 1?
Uh-huh.
Yeah.
Instead of saying that it's equals to?
I'm glad you brought up that question. So because we're using an ideal model, and it's kind of like what exactly happens here. So for example, it's the same sort of question about, let's say if we didn't have the diode, is what happens at Vn exactly equal to 0. We said that Vn is greater than 0, the diode is an on switch. At Vn less than 0, the diode is an off switch. So we kind of didn't say what happens at Vn equal to 0. And because of this ideal diode isn't really something that happens, we have this really, it's sort of it's a discontinuity, let's say, between Vn being like, you know, a very, very small negative value to Vn being a very, very small positive value. So because of that, in this ideal model, we assume that when Vn is equal to 0, when Vn is equal to 0, the diode is on still.
Okay.
Yeah. And then, you know, what happens is when Vn equal to 0, at exactly equal to Vn equal to 0, the diode is on, but because Vn itself is 0, Vn is the voltage across the diode, okay? So you have a switch, it's on, but the voltage across the switch is 0. Means at Vn equal to 0, you still get 0 current. All the switch is on. Does that make sense? But as soon as Vn goes to a tiny bit over 0, the current just pegs. The current goes to an infinite current. Did that make sense, Manuel? So when you have a switch, it could be closed, but if the voltage across the switch, or VD, I'm going to say, is equal to 0, if the voltage is 0, you can't get any current across this switch. Even though the resistance, even though resistance is 0, you still get no current. But as soon as VD, I don't know, goes to 1 times 10 to the minus 1,000 or whatever, as soon as it goes a little bit over 0, the current just goes to infinity, basically. And again, this is sort of a function of our model, but we'll see in some of the examples, you actually have to assume that when Vn is exactly equal to 0, then the diode is on. So,
Professor,
Yeah.
I guess mathematically makes sense because if we have 0 over 0, it's infinity. So pretty much I equals 0 volts, 0 resistance equals infinite. I guess mathematically speaking would make sense.
Okay.
Since you already wrote down that, I think I'm gonna remember it that way.
Okay. Cool. Ooh, okay, guys, I think I took a little bit longer than I thought to get to this point, but we're out of time. So we're going to stop here and just have a good weekend. And hopefully it'll, by next Tuesday, the fires will be out, knock wood. Okay, guys, any questions?
No, I was just going to say thank you, Professor, for explaining everything. I really appreciate that.
My pleasure. I'm glad it worked.
Thank you, Professor.
Thanks. Take care.
Thank you.
Thanks. Bye.
Professor.
Thanks, Professor.
Professor.
Thanks.
Hello.
Yeah, Absalom?
Yeah. Can I just talk to you and just like at the end of everything? I just
Sure.
have
Yeah.
a question. I just have a quick question.
Sure.
Thank you. Thank you.
Go ahead, shoot. Or do you want to, is it a private question or do you have a?
Kinda.
Okay. Why don't you do this? I did not give you guys or I might have had my cell phone, but do you have something to write on?
Yes.
So why don't you give me a call on my cell phone, and it's 858-349.
Professor, you're recording right now. You might not want to stop recording it just real quick.
Yeah. No, it's okay. You guys can have my number. Thanks, Juan.
Oh, okay, you got it.
But thank you. So it's 858-349. 3132.
3132. Okay. Well, I mean, I guess I could tell you about it. Okay, so I had to change my classes. Two of them. And I was pretty much like, will be like 2 weeks behind on those classes. So I had to catch up. I kind of like fall behind on this one. I've been trying to catch up with the videos and everything. But I don't know if the videos are behind because there's always one missing. Like, for example, I don't think there's the one from Tuesday.
Yeah, sorry. I actually just put that up this afternoon.
Because so like what happens, like at least with me, is this is just personal preference, okay? That like I don't like PowerPoint because I always fall behind in every single class that has PowerPoint. But I know it's okay if that's your method. Like I will find like something around it, so don't worry about that.
Yeah.
So therefore I'll go back on the videos and then like go on my own pace, understand everything, and that's the way I do it. But like now what's going on is that when I come to class, I'm kind of lost because I don't have the background of previous classes or the previous class because it's not up yet on YouTube. So like is there like thing that you recommend to be more efficient on PowerPoints as a personal opinion or professional opinion?
Nah, man. If you don't like I don't blame you. If you don't like PowerPoints, you don't like PowerPoints. You know what I'll do is I've been sort of lagging on putting up the videos, so I'll just I might fail here and there, but I'll promise you basically from now on, I'll just upload the videos right after the class. So every class we have, so you'll just be caught, basically you get them live like that night. So like I'll upload it tonight.
Okay. Yeah.
Okay.
I think it would just be like the catch up, and then after that, like I will be
sure. No, makes sense.
in sync with you in the class and everything.
Yeah, makes sense, man. You
right.
You guys got a tough load.
All right. Thank you very much, Professor.
Okay. Good luck. Take care.
Thank
you too. Bye.
face to face.
باید دقیقا میتونید صبر کنید. بله قربان. دقیقا صبر کنید با.
Are you in the middle of your class or something?
Yes, sir. Let me just finish